Hello everyone, I am Haiyin Che from Institute of Data Science and Knowledge Engineering, School of Computer Science in Beijing Institute of Technology. In last session, we learned three main recommendation system algorithms: user-based filtering, item-based filtering, and content-based filtering. And in this session, we will learn a typical latent factor model, matrix factorization. Let's watch a video how recommender system works.
In 2006, Netflix famously offered a prize to solve a simple problem which had been around for years. All online commerce giants are fighting to get better at solving this same problem. Given observations of a user's past behavior, predict which other things that same user will like. For example, based on Alice's viewing history, will she like The Matrix or Grapes of Wrath? We can represent user preferences graphically as connections between people on one side and things on the other, such as movies. Here, the strength of connection is visually represented by the thickness of the lines. So the problem is to fill out all of these missing connections we don't yet know, shown in red. But because of the messy, unpredictable nature of people's tastes, we can never perfectly predict what they will like. Because, for one, it involves a guess about the future, based on something you've never seen. And two, the answer is always in flux, because people's tastes change over time. What we can do is try to estimate those values as best we can, using whatever data we have access to. So, regardless of the context, we can describe the problem in the following mathematical form. We use a matrix, which is a collection of numbers organized into rows and columns, where the rows are users and the columns are items, in this case movies. And each cell in this matrix contains a number that describes how much each individual likes each movie. For example, we could use a scale from 0 to 4, where 0 would represent I hate it, 2 is neutral, and 4 is I love it. At any given moment, there will be some set of preference data for users and movies, but it will be incomplete because users have only seen and rated a few movies each. And so the problem boils down to trying to predict these missing values. How should we make these predictions? There are two general approaches to this problem. The first is called content filtering, which is to use information we know about people and things as connective tissue for recommendations. It's like asking Alice questions about what kinds of movies she likes to figure out if she will like The Matrix. It begins by labeling each person and movies with some known attributes, or what we call features, for example, action and comedy. That means if Alice likes comedy and hates action, we can represent her as 3-0. Each movie is also mapped to each feature in the same way. For example, The Matrix has no comedy and lots of action, so we could represent it as 0-4. And to determine whether someone will like a movie, we need to multiply these factors together. So we could represent the strength of connection between Alice and The Matrix as 3 times 0 plus 0 times 4 equals 0. So our estimation is that she will hate the movie. So to make our predictions, we first need to gather this feature data for every user and movie. To simplify, let's return to a matrix representation. We can store this information in two matrices. One defines the mapping between people and features. The other defines the mapping between movies and features. And by multiplying these two matrices together, using matrix multiplication, we get an estimated strength of connection between every person and movie. And if we'd like, we can normalize our data to make sure the scale stays between 0 and 4 by dividing all values by 8 and rounding to the nearest 0.5. That's one way to solve this problem, known as content filtering. The problem is, it's overly simplistic and not very accurate. That's because there are obviously more relevant features of a movie than just comedy or action. The obvious way to improve this is just to include more features. If you recall, when Netflix started, it did just this. It would ask new users to fill out a laundry list of questions about their preferences before presenting them with suggested movies. And this leads to the problem of having to collect all of this preference data on users. Not only is it a burden for users, it's also prone to failure, as we aren't always great at describing our own preferences. Sometimes we simply can't explain why we like things. We just do. Which brings us to the other approach, called collaborative filtering. The motivation for collaborative filtering comes from the idea that you will probably like things people with similar viewing habits also like. This idea was popularized in this 2009 paper by Cohen, Bell, and Volinsky. So to begin, we can throw away the idea of dreaming up features used to connect people in movies. Instead, we flip things around and use the user preference data we do have to generate the features. For example, we might have this incomplete set of preference data, and we will instead learn or discover the relevant features based on patterns in this data. And this is done by simply reversing the problem. We first perform an approximate factorization into two matrices. And we can do this using a machine learning approach. The job of the machine learning algorithm is to guess values for those matrices, which will match the existing data in the preference matrix as closely as possible. The simplest approach is to simply guess numbers over and over until you arrive at a set of numbers which predict the data with the lowest error overall. Once this estimation is finished, we can multiply the matrices as before to fill in all of the missing values. And it's important to note that we won't know exactly what to label these discovered features, so we call them latent features because they arise out of the underlying patterns in the data. You can think of them as an average or weighted sum of the patterns in the data. They are not based on a human-defined feature, such as comedy. And that's the key insight behind this method. With content filtering, the features come from the human mind, whereas with collaborative filtering, the features are extracted directly from the patterns in the data. And this will predict the data in the same way but more accurately. It's also important to notice that this kind of prediction is actually a form of compression, because we can represent a huge matrix of preference data by two smaller matrices of feature data. And once our feature data is determined or learned, we can throw away the original data we started with, because we can simply multiply the features together to recreate that data. And the reason this is possible is because the preference data we started with is not random, but follow patterns which exist across people. If instead the preference data was filled with random numbers, we would not be able to compress it accurately because there would be no patterns to extract. This collaborative filtering approach has also been applied to a wide range of contexts, such as evaluating policy outcomes before they are implemented in the real world, known as synthetic control. For example, if we wanted to understand the effect of gun control or minimum wage increases in some city, we could look at the effect in similar cities first which have implemented those policies to approximate the outcome using the same mechanism. So it is the patterns we share that allow this method to work. Recommendation systems based on these ideas are in widespread use today, whether it's movies, music, news articles, or anything else you search for online. The things that are recommended to you are based on patterns the machine has observed in other people who are similar to yourself.
From the video, we know there is a hidden patterns in the rating matrix. We want to find some character the items may have, and we decompose the rating matrix into item character rating and user character rating matrix. Moreover, we don't want to know the meaning of the characters, which is abstract model. We just supposed the number of characters. The linear algebra, the singular value decomposition SVD, is a factorization of a real or complex matrix. It generalizes the eigendecomposition of a square normal matrix with an orthogonal eigenbasis to any M plus n matrix. It generalizes the eigendecomposition of a square normal matrix with an orthonormal eigenbasis to any m-to-n matrix. It is related to the polar decomposition, especially the singular value decomposition of an m-to-n complex matrix M is a factorization of the form U sigma V asterisk, where U is an M-to-M complex unitary matrix. Sigma is an M-to-N rectangular diagonal matrix with non-negative real number on the diagonal, and V is an N-to-N complex unitary matrix. If M is real, U and V can also be guaranteed to be real orthogonal matrices. In such contexts, the SVD is often denoted U sigma V transpose. SVD requires a dense matrix, that is, the matrix doesn't have missing value. Evidently, user atom rating matrix has lots of missing value, so use matrix decomposition to replace SVD. Decompose the matrix into two matrices, that is, R equals to P times Q, where R is M-to-N user item rating matrix, P is M-to-K user latent factor matrix, and Q is K-to-N item latent factor matrix. For U user and I atom, their rating is, if get two dense matrices P and Q from R equals to P times Q, we can predict the missing value in R. So how to calculate P and Q? Define cost function as shown in the formula and use the cost function to evaluate the better choice of P and Q. We only calculate cost function with the already given rating values by the user. The first part in the cost function is the MSE of the predicted rating value RUI hat and true value RUA. And the second part in the cost function is regular value, which prevent overfitting. We do the iteration to minimize the cost function. There are two ways to minimize the cost function. The first one is using ALS, alternating least square, to minimize cost function, which means fix P compute Q to make C minimize. Then fix Q compute P to make cost function minimize. Until reach max iteration or C satisfies the threshold condition. Compute partial derivative of C with respect to Pu and make the formula equals to 0, get Q. Similarly, get P. Second, using gradient descent to minimize cost function, which means compute partial derivative of C with respect to Pu and the partial derivative of C with respect to Qi. Then do iteration using the formula in the slides, where alpha is the step size. After each iteration, the Pu and Qi are updated until the end, until reach max iteration or C satisfies the threshold condition. To understand the recommendation system, a series of experiments were designed. It included user-based theating recommendation and matrix decomposition. In user-based theating recommendation, it consists pre-processing and collaborative filtering. In 1.1 preprocessing, it includes load the data and relate the two original tables and create a new data CSV file and make a dictionary by deleting the duplicate records. In 1.2 part, collaborative filtering, first compute the user similarity and then list top 10 similar users to the current user and make the recommendation. For matrix decomposition experiment, we need to import the library supplies. The used dataset include 100,000 users rating on movies. The related models include Func or Bias SVD, grid search for training. The goal is to train and test on the best model and get the best parameters for SVD. The process will be: first, import library, second, import data, third, grid search SVD training, fourth, use the best parameters obtained by grid search for training and prediction, and finally, visualize the result. All the experiments material, including the manual and the codes, are provided on the platform, which can help you to do the hands-on. In this session, we learned a typical latent factor model, matrix factorization. Thank you for your attention. If you have any question, feel free to contact me.